Hello and welcome. I am Truls Nordby. I am professor at University of Oslo and also founder of Murex, a company which is making the ProboStat sample holder for electrical measurements at high temperatures. In this presentation, I will show the main features and applications of the ProboStat. First, let's ask what is a ProboStat. A ProboStat is a sample holder. Quite simply, it is a very versatile one. It is made primarily for high temperatures, so that the ProboStat, for that purpose, will sit in a furnace. And it is made for controlled atmospheres. It has an enclosing tube. Inside you can hold an atmosphere that you may make, for instance, with gas mixers, like the Humistat gas mixer that we make. The heart and core of the ProboStat is the base unit, which we see here. It has feed-throughs for 4 electrodes and 3 thermocouples. It has in and outlets for 2 gas streams, and it has several fixations and a spring load system for holding everything in place. The main features of the ProboStat is, as I said, it can support up to 4 electrodes. It has 2 separate gas chambers, and it has up to 3 thermocouples. It can work from room temperature up to 1600 degrees centigrade. So it's suitable for studying ceramics, metals, polymers, salts, and so forth. It can hold a controlled atmosphere, and it can tolerate oxidizing, inert, reducing, and corrosive gases. It can operate in dry atmospheres or wet atmospheres, or even in steam. And the total pressure can be from 1 bar and up to 20 bars. It has replaceable hot zone parts and spring-loaded contacts. This enables you to attach several of these electrode contacts that come in the ProboStat system when you buy it to feed through contacts here, and you can take them off and put new ons and lead them up to the sample, which sits here at high temperature. It is typically doing 2 electrode or 4-point conductivity measurements. It can do 3 electrode polarization studies. It can be used for single button or tube fuel cell or electrolyzer tests. And it is very suitable for EMF transport number measurements and Seebeck coefficient measurements. But it has also several additional options, like thin films. It can measure on liquid or melting samples, 4-leg TEG module testing, high voltages for plasma catalytic bed reactor, a heated base unit for steam, and so forth. Let's start and go through it in more detail with the ProboStat base unit. The base unit has a stainless steel core, as we can see here. It has 16 electrical feed-throughs organized on a pedestal, 4 feed-throughs here, and 12 feed-throughs around here. Here it's a schematic of the feed-throughs and the gas inlets and outlets on the outer and the inner chamber. It has a high temperature O-ring sealed support that is fastened here. And it has an O-ring sealing to an outer tube that sits here. The 16 feed-throughs are gold-plated nickel mini contacts, which are plugged in to a high temperature polymer insulator. It has type S, which is platinum or platinum 10 rhodium, or type K compensation wires from this feed-through throughout to the thermocouple sockets. It has spring loads for contacts and sample sealing, so you can fasten the springs to this rim here. It has 4 gas lines, 2 in and 2 out, and it has cooling water and a fixation flange around here where you can supply cooling water and also fix the base unit to a stand, for instance. And underneath, it has an aluminium hexagonal housing. This has 6 BNC electrode connect sockets, as you can see here. It has ground and shield switches here. It has 3 thermocouple sockets, type S or K, and it has the 4 Swagelok quick connects for gases in and out. We can have different outer tubes and lengths. Here you see one of the layers in an extended ProboStat system, coming with 1 alumina tube and 2 quartz tubes in this case. The alumina tubes allows you to go to 1600 degrees centigrade. Quartz tubes can go to around 1000 degrees. We can also supply a super alloy 253 Ma, which can go to 1100 degrees and hold high pressures. And also ordinary stainless steel, which can go to 800. These metallic tubes of the superalloy or stainless steel, they can reduce the external noise by shielding. And this flanged version here can also then hold up to 20 bars of pressure inside the ProboStat. They come in a full length, which then has an outer tube of 60 centimeters. But you can also get them in shorter versions for lower temperatures. They are more convenient when they are shorter. For instance, 50 centimeter long, like this one, or even 40 centimeter or 30 centimeter. And then all the furnishing inside is correspondingly 10 or 20 or 30 centimeters shorter. Then we have the sample support tubes that sits in the middle of the ProboStat. Here the sample support tube comes up and holds the disk sample. The standard material is a pure dense alumina. It is glued to a socket that allows you to fix it to the ProboStat base unit using a high temperature cement that can tolerate up to 300 degrees. In this case, you see an extended set being supplied with several support tubes with their sockets. The support tubes come in typically 10 to 20 millimeter diameter. The biggest is 24, and they come then in different lengths depending on the length of the ProboStat system. You can also get the support tubes in other materials options like YZ or quartz or stainless steel, depending on your needs. We have also a bar sample alumina support tube, which has a slit for bar samples that fit in there, pressed down with the roof part and against a floor part. Here you see a side view of the bar sample sitting between the roof and the floor, as we call them, with contacts in both ends for SEBIC measurements in this case. And here you see a real picture of a real sample in a real setup. You see the spring load is holding the roof down, pressing to the sample against the floor. The spring load system of the ProboStat is a rather unique thing. It is made of only alumina and platinum parts in the hot zone and therefore can tolerate up to 1600 degrees centigrade. Then we have alumina rods that go down, and then we have steel springs sitting in the cold zone, hooked down to the pedestal. And here you see the spring load in a real cell. There are also special versions of the spring load for Van der Pol assemblies and for thin film assemblies. The ProboStat has a good atmosphere control. It has 2 gas chambers One is inside this support tube and feeding to the bottom electrode, and one is on the outside, inside this outer enclosing tube, feeding the top electrode. You can use it in single or dual atmosphere operation, and there are separate tubes for the inner coming on the inside and the outer gas. In this case, a bent quartz tube that supplies the outer gas directly to the sample inside here. The sealing that is between the two chambers here can be done with gold, with silver, with mica, vermiculite, a glass. You can use Aramco and different ones. Each different type of seal have different advantages and challenges. You can use any gas in a ProboStat. It can go up to 20 bars, as I said, but it can also hold a low vacuum. It is conveniently connected to gas lines with quick connects, 2 in and 2 out. To establish the atmosphere, you typically use gas mixers and humidifiers, but you can also monitor the oxygen activity inside the ProboStat with a miniature oxygen sensor that we can provide. The electrode connects and thermocouples come in many different fashions. Here you see an overview of many of them. They can be simple 1 or 2 wire contacts. They can be point contacts like these or these. They can be hand contacts, as we call them, and they can be hand contacts with nets like this. Here you see some real cases. You see hand contacts with net, and you see ring contact. You see spare nets, and here you also see some gaskets for sealing. We have spare nets that you can clip on like this. When the first one is used, you can clip on a new one to save the cost of the wires. We have van der Poel assemblies. You can see them here with the four contacts for the van der Poel measurements. And you can get all of these in other metals like gold, silver, nickel, or copper, or most of them, we can say. Then we have the thermocouples. Here you see different thermocouples for the different positions in the cell. They can be of type S or type K. The positions are top, over the sample, control, at the sample, and bottom under the sample. And all these are then adjusted in length, depending on the length of your ProboStat system. The setup schematics of all the parts inside the ProboStat can look typically like this. Setups like this are all provided in a manual, and when you follow a setup like this, you see how and in which order you mount things like the inner gas supply tube, the inner thermocouple, the inner electrode or lower electrode or a point electrode on contacting the bottom of the sample, the bottom electrode. The support tube then comes next. Then you add the sample and you put on the top electrode, and then the spring load, the outer thermocouple, and the outer gas tube. And here is shown where they are connected to what kind of instruments, and the numbering refers to the feed-throughs at the bottom of the base unit. The manual also provides instructions for your own fabrication of replacement parts for these things that go in the hot zone. If we talk about the different types of measurements in a ProboStat, here's a little overview. The typical types of measurements are measurements on disk samples in single atmosphere. They will be 2 electrode or 4-point van der Poel conductivity measurements, or they can be 3 electrode polarization measurements. Here you see an example of a 3 electrode sample. They can be disk samples which are sealed and therefore operated in dual atmospheres, and this is then for fuel cells or electrolyzer studies, or EMF transport number studies or permeation studies. We can also use bar samples, and these are then used for 4-point conductivity or Seebeck coefficient measurements. There are also other geometries, like tubular samples, film samples, or even melts. And ProboStat can also be used for other types of things, like annealing samples, establishing high voltage plasma, measuring dielectric breakdown, things like that. I would like to say a few things special on 3 electrode measurements, which are very convenient in a ProboStat. With these, you can do studies of electrode polarization using electrochemical impedance spectroscopy or voltammetry or combinations of these. There are several possibilities of how to make 3 electrodes on samples that go into a ProboStat. Here you see an example of a ring reference electrode, of a small reference electrode, or an embedded reference electrode, and how they are connected in the ProboStat in each case. This is taken from the ProboStat manual. But as you may know, the validity of reference electrodes in solid-state electrochemistry is still ambiguous and depends on the detail of the geometry here. Electrochemical impedance spectroscopy is very conveniently done in a ProboStat, typically AC conductivity measurements or grain boundary resistance taken from the impedance spectrum here, or electrode impedances at low frequencies, where you can typically delineate charge transfer and mass transfer impedances. Here is a typical impedance circuit diagram for a ceramic solid electrolyte sample. The ProboStat works well with all brands and types of impedance spectrometers and potentiostats because the ProboStat is, after all, a passive cell, so that it works well with all instruments. You should be aware, though, that there are some differences in how you connect the shields, or rather how you don't connect shields, depending on which instrument you use. To take an example, if you connect your sample directly to a Solitron 1260 impedance spectrometer, you need to connect the shields together. But if you connect your sample to a potentiostat, like this Solitron 1287, then you must not connect the shields together because it has driven shields. So this is something to be aware of. But the ProboStat can do it all. We can supply thin film assemblies. The thin film assembly sits here on top of the support tube. It is very fragile and has very small forces because the thin film on top of this substrate here is typically very easily scratched to pieces, so that this is not easy to use, but it is possible to use it. So we have in-plane setup where we have an insulating substrate, and you have 2 or 4 electrodes touching the sample, and you measure in the sample. And you have a through-plane setup where a top electrode measures through the sample down to the conducting support plate made of platinum. I would like to mention also a quite new development in electrical conductivity measurements, namely surface protonics. There is recently an interest both in studying and using the proton conductivity on surfaces in porous ceramics and ceramics in general. This is an emerging field, and the ProboStat is very well suited for these kind of studies. You use impedance spectroscopy to do the measurements in controlled water vapor partial pressures, typically from very dry to very wet atmospheres or even in steam. Here are some examples. Here is a recent paper from this year by Shalan Kang and co-workers from my laboratory in Oslo, where she has measured bulk conductivity and the conductivity in the chemisorb layer and the first physisorb layer and the liquid-like physisorb layer as a function of temperature. and these are then protonic surface conduction on a sample of TiO2. You can see that you go very close to room temperature in these measurements, typically. And I would like to point out that temperature control all the way down to room temperature, even with big furnaces, is possible with a ProboStat if you set the PID properly on your temperature control. Here is another study on zirconia, showing the different conductivities as a function of inverse temperature again, on samples sintered differently, therefore with different grain sizes and porosities. And it is interesting to see how conductivities can vary by many orders of magnitude as a function of temperature and microstructure of the sample. These measurements are done in collaboration between Suzhou University in China and Oslo University in Norway. You can use the ProboStat for insulating materials and dielectrics at very high temperatures also. The ProboStat has a large cell impedance, so you can measure insulating samples and samples with low capacitances. It requires that you operate your seals properly, and you can, for instance, use dry atmospheres to reduce surface conduction and capacitance by water. You can also use driven shield to guard against parasitic conductance. You can use AC and DC combinations, but the ProboStat is typically limited in frequency up to 10 megahertz. You can do polling and breakdown studies at high DC voltages up to 10 kilovolt in the high voltage version of the ProboStat. Here I show you a custom-made ProboStat with a wider part here, so you can use a wider enclosing tube, and therefore you can also have a wider sample up here. So this was made for a customer who was interested in studying dielectric properties and breakdown on big circular wafer samples. The ProboStat was developed for and is very well suited for EMF transport number measurements, where you establish dual atmospheres and measure the EMF, the electromotive force, and from that obtain the ionic transport number. Then you set the cell up like this. You have your sample in here, you supply one gas to the top and one gas inside to the bottom electrode, and you measure the voltage over there. This is typically used to study oxide ion transport numbers, but you can also study proton transport numbers by using different water vapor or hydrogen partial pressures. And the ProboStat can, of course, also be used to do hydrogen deuterium isotope shift measurements to get further information about proton transport. There are many papers on how the ProboStat is used for these kind of measurements. We can also do solid oxide fuel cell tests in a ProboStat. Here you see in the animation how we start with a support tube. Here we put on the inner electrode, we put it flat like that, put on the sealing ring, put on the sample. Here comes the top electrode, we bend it down. Here comes the thermocouple, we cover the thermocouple, then we put on the spring load, and we put the top gas in at the end. There are commercial thin electrolyte samples available if you want to buy them to try it out. Here are some pictures of samples from fuel cell materials in the US, or next series as it is called now. Here you see electrolyte supported samples, and here you see anode supported samples with a smaller cathode that then goes to the bottom electrode in a ProboStat. If you want to do it like we show in animation here with a gold sealing ring, that is nice and clean, but you have to bring the gold to 1060 degrees to make it soft enough to seal properly, and it's quite difficult to do. You need some practice. A recent development is the polymer electrolyte membrane for electrode head for ProboStat for measuring the conductivity of polymer films, putting them on here, having 4 wire electrodes. And you can then put this on top of the support tube in the ProboStat. It has a peak construction here, so that it tolerates up to 200 degrees. So compared to other cells for studying polymer electrolytes, the ProboStat can do it at higher temperatures, up to 200 degrees. This perforated plate holds the sample down and allows equilibrium with the gas phase, and it's held down by the spring force. The temperature is monitored accurately by a thermocouple that comes up inside here and sits just under the surface here. ProboStat is suitable for various measurements involving thermoelectrics. Firstly, to measure the Seebeck coefficient in a temperature gradient. For this, we typically use a bar sample where we have a higher temperature here and a lower temperature here, and we measure the voltage over it and get the Seebeck coefficient. One can also use disk samples. Here's a disk sample, and you use various contacts to measure both the conductivity and the Seebeck coefficient, and various heaters to create the temperature gradient. We have also recently developed a 4-leg thermoelectric generator module test. The unit, the test module, sits here on top of a support tube in the ProboStat. This support tube is now a closed steel tube that we flush with water so that we keep a temperature around between room temperature and 100 degrees here. And on top, we can have a very high temperature from a furnace so that we can create over the legs sitting here, 1, 2, 3, 4 legs here. We can have a temperature gradient of up to 600 degrees. And we can go up to 1,000 degrees here on the outside. So in this way, we can use the ProboStat to study thermoelectrics at much higher temperatures than other sample holders. And we can study interconnects, for instance, between the legs. Here are some results from a recent paper showing the open circuit voltage of the 4-leg module as a function of temperature difference and the top temperature. And here we plot the resistance of the module and the output power as a function also of the temperature difference and the top temperature. You can also use the ProboStat now as a fixed bed reactor. You can mount the bed tube that we are making now in the place of a support tube. The materials of the tube and the frit here are glass or quartz, and the frits we put here under the sample is a standard type 1 to 5. You can send the gas now through your catalyst bed from the top to the bottom or vice versa. You can have 1 or 2 or 3 thermocouples to monitor the temperature here. And you can have different electrodes. You can put electrodes here at the bottom of your catalyst support. And you can put another electrode on top and study the effect of electrical fields. And for instance, create a plasma through the catalyst and study the enhancement in catalysis by the plasma. Finally, there are many more options and auxiliaries for the ProboStat. The base unit, as I have maybe mentioned before, can be heated. There's a heated version of the base unit so that this part is heated and this part is colder. And therefore, via the heated part, you can supply steam and liquids that need to be kept in gas form by heating it up to 165 degrees. There is also a high voltage version of the base unit, allowing you to feed up to 10 kilovolts through the base unit. You typically need tubular furnaces to heat the ProboStat up. Here you see a version from Thermconcept in Germany, and here you see a Chinese furnace from BYT, which is very cost efficient and has very nice temperature control all the way down to room temperature and up to, for instance, 1200 degrees in the case of this small furnace here. You will typically need gas mixers and humidifiers like our Humistat that can mix two gases and add up to 100% steam. You need instrumentation, of course, like impedance spectrometers, potentiostat, multimeters, and you can use any brand and type, and here are some of them. Murex also makes a software, Omega, which is very versatile, has a bit high threshold for starting to use it, but when you learn to use it, it can do virtually anything. It can control many instruments. Connected to the ProboStat, can control the gas mixer. You can monitor many properties as a function of time, as for instance temperature increases and things happen. Or you can make different gas mixtures and measure the conductivity in different gas mixtures automatically without attention from the user. So with that, I thank you for your attention. If you have questions or comments or inquiries, you're very welcome to contact me personally or Norex at this email address, or to look up many things at the Norex website. Thank you very much.